Simple Harmonic Motion by Yana, Davin, Jack, and Sinkavi. So, simple harmonic motion occurs when there's a restoring force on an object that's proportional to the displacement from the equilibrium. This is the equation for an object undergoing simple harmonic motion. Y of t equals a sine of omega t plus. Okay, so once you have that, you're pretty much set. And then to solve for omega, you have omega equals 2 pi f. And then another equation you might need is to find the period. The period is the length of time it takes for an object to complete one cycle. So, t equals time over cycles. The period can also be expressed as an equation that's proportional to the angular frequency. T also equals 2 pi over omega. And frequency is the number of cycles that the object that you're looking at completes in 1 unit of time. So then we have equals 1 over t cycles over time. And an object undergoing simple harmonic motion typically transforms potential energy to kinetic energy, and then back to potential energy, and so on. It's a repeating cycle. So total energy equals K plus U, where K equals 1/2 mv squared, and U equals kx squared, where K is the constant.
Oh, we're talking about the spring?
Yeah.
This U usually means gravitational potential energy, sorry.
Right? 1/2 kx squared?
Yeah, go on.
Is that too hard to edit?
No, I can.
Okay, work some magic. So some problems involving simple harmonic motion that you may encounter on the AP are a mass oscillating on a spring, a simple pendulum, or a physical pendulum. And we are going to have an example of one of those problems now.
Okay, start action, go.
Go.
Okay, so the problem that we have set up here, we've got a mass on a pendulum, and the mass is m, and it's dropped from an angle theta, and it strikes a box of mass m, and this box, there's a spring between this and a wall, so the wall is obviously going to be stationary, and as soon as this mass strikes this box, it sticks to it, and the string detaches. The reason we picked this problem was because it has both a spring oscillation, and a pendulum. So it sort of brings those two concepts together, and it shows that they're pretty much the same thing actually. So the first what we've got to do here, in part A, we're finding the time that it takes for the mass to reach its maximum compression. And to find that time, we've got to calculate the time it takes for this to swing down and hit the box, and then for these two to reach maximum compression. So what we're going to do here, since we know that the time it takes for the pendulum to get from here to here would be 1/4 of its period, we can say that T, call this P for pendulum, equals 1/4 of its period. And of course, the period for a pendulum is T equals 2 pi square root of L over G. That's kind of like how the period for a spring is M over K, or the square root of M over K. And then we're going to take that, and then we're also going to use the period of the spring with the two masses, and that's going to be T equals 2 pi times the square root of 2m over k, and we're using 2m because it's not just this part is sticking to that. So it would be 1/4 the total time for it to take its maximum to reach the maximum compression would be t equals 1/4 2 pi square root of L over G plus 2 pi square root of 2m over k. Well, this is also times 1/4, by the way, because the time it takes to get from here to here would be 1/4 of its period as well. And then we can factor out the 2 pi. So, and we can also factor out the 1/4. So we've got t equals pi over 2 times square root of L over G plus 2m over k. Pretty simple. Okay. The next part, we're going to need to use a little bit of energy. So, we can write E initial equals E final, since there wasn't any outside forces acting on the system to take away energy. And then we're going to use our simple harmonic equation for a pendulum. mg L minus L cosine theta equals 1/2 mv squared. So here's the potential energy, and here's the that's what it equals, 1/2 mv squared, so we're going to use that to get the velocity. So we end up getting that v equals the square root of 2gl times 1 minus cosine of theta. So we're also going to need to apply the momentum conservation to find the speed of the masses just after the collision. So we know that the initial momentum would be mv, and we get v from here, and that would equal 2 mv final. And this is the initial. And this is also v initial, just for further clarification there. So, we've got v equals v final, that is 1/2 square root of 2gl 1 minus cosine of theta. And then we're going to use energy to determine the maximum compression. So, going back to our EI, EF, we've got 1/2 2m v squared equals 1/2 k a squared. And then, with a simple rearrangement, we get a equals square root of mgl 1 minus cosine of theta over k. And there we have it. That's the amplitude.